Hi all. Um, so this is that's my first. In fact, I start posting this video and I had to stop a couple of times. And I at the end of it, and what you're seeing here is the end, the last problem. I realize I haven't told you. Probably I did in class, but perhaps not all of you were there. Um, how do I recommend? I mean, what's the best way to learn physics? Again, physics is not okay. I need to know which equation to use and I need to apply. I mean, it is that, but that's the last step in solving problems. The first step is to have a clear vision or understanding of what the problem exactly is. And that's when I say, okay, smell the problem. Try to identify if your problem has acceleration or is a projectile motion or is one that is a free fall. Those are the situations we saw: free fall, projectile motion, or motion that has one specific acceleration or rotation. So those are the situations you have to think about it. Okay. Um, Now, once you identify the problem, what do you do if you are studying? So if you are studying, don't worry about equations. I will give you the equations. And in the exam, if you need equation, they are not given in the paper, or if it's missing a constant or something, you ask me, I will give it to you. But here's the situation. Um, you need to know how to ask for an equation. You cannot show me the problem and say, hey, I wanted the equation to solve this problem. That's not it. You say, okay, I wanted the equation that gives displacement with acceleration in an acceleration type of motion. What is the equation for velocity and acceleration in one dimension? And then I can give you, it's not a problem, okay? But again, so you're gonna have your cheat sheet as you have right now when you were studying. Now, when you study, in order to learn, you really have to test yourself. It's not enough to read the problem and then look straight to the solution and then repeat the steps. You're not learning. You are pretty much repeating what somebody did. You are doing the automatic steps. So the best thing to do is, okay, you go to the book, you open, you have the problem solved, or you have your homework that you have some online tutoring going on, or you have the problems that I did in class. So I think we had enough problem solved in different situations solved presented to you. So now is your time to study yourself, to test yourself. How do you do that? You read the problem and try to do. Pretend you are in a test environment. Um, Now, if you try several steps and you can't get a solution to it, then you go and try to solve yourself, right? But give yourself some time. Trust yourself. 5 minutes, 10 minutes, and then you go for it. Now, if these videos here, if you attempt to memorize solutions, you can't do it. You can't do it. Memorization is not an issue in physics. Is an understanding of how what's the situation is, and once the situation is understood, what equation should I apply, and then you have to go through 3 or 4 equations we learn. Does the motion has not acceleration? Is the one that the velocity is constant or not? Am I asking for magnitude? Am I asking for am I being asked to add vectors or not? Okay. And as always, I will be checking mail over the weekend, so you can ask me for help if that can be done. Okay. All right. All right. Let's go. So the first one is a vector pointing, okay, the difference between magnitude, which is the number. So magnitude is equivalent to a number, right? Now vectors, to be fully defined, require magnitude, require a number, plus orientation, direction, okay? So we gotta have both. So if you are talking about magnitude, you're talking about a number. A number is always positive, like at 10 seconds, 1 hour. You don't say negative 1 hour, is always positive. So it's a vector is pointing upward and has a positive magnitude. A vector pointing downward has a negative magnitude. I mean, it's always, magnitude is always positive. So a vector pointing upward has a positive magnitude, let's say plus 10 newtons, right? This plus is not because of magnitude, is the direction if you call it a positive upward direction. And therefore, this vector is one that is indicated by, let's say, negative 10 Newton magnitude. This negative is associated with the orientation, not with the number. So magnitude cannot be negative. Two displacement vectors have magnitude 5 and 7 respectively. If these two vectors are added together, the magnitude. So we saw that in class. So let's say one is this, the other one is that. Then the resultant is 12. Or if you one is this, and the other one is that, the resultant is 2, right? So which means the magnitude are in between those two numbers, basically, 2 and 12. We also saw that in class. So when you think about acceleration, wait a second, where do I get color? There you go. No, over here, yeah. So for instance, this acceleration vector projects along v with a dot. So basically you don't have acceleration along the direction of v. So how do you figure what's going on here? You compare. So velocity v and acceleration have the same direction. So the direction is the same. So you have a speeding up situation. Or if you have the velocity vector and the acceleration vector in opposite orientation, right? Then you have a slowing down situation. Now you learn about forces, and then you know acceleration is a quantity associated with force. So if you have a velocity vector in this direction, and if your acceleration vector is along this direction, you can also say, because of that, what we learned today, F is equal ma. So the direction of acceleration is the same as that of the net force, which means, so the car goes down in that direction, but there is a force that is holding up, that is preventing the car to speed up. So it's a force responsible for slowing down the car, okay? So what you need to do in this exercise is to determine how this net acceleration projects along the direction of your velocity vector. So if you have this acceleration vector here, you have this plus that. So this A acceleration is essentially this plus that. So which means you have a slowing down here, slowing down, and this body at that moment is being pulled in that direction. Okay, so this acceleration here, so you have one projection. Let me just extend it. That's your acceleration vector. So there is one projection along this direction, which means you have a speeding up and the body is going to its left hand side, right? It's being pulled in that direction. So here, acceleration has one component that goes along the direction of velocity vector, but look at the other projection. It's to the right, okay? So you have a speeding up, and the body pulls that way. Here you have also a speeding up, and the body is pulling that way. And here we have a simple slowing down. A rock is thrown from the upper edge of a tall cliff at some angle above the horizontal. It reaches its highest point and starts falling down. It reaches its highest point and starts falling down. So you have a building, right? And then you have something like this. Highest point right there. Which of the following statements about the rock's motion are true just before it hits the ground? So let's say the ground is over there. So right before reaching the ground, the velocity vector is tangent to the path. It has two components. One is the Vx, right? And the other one is Vy. And here my drawing is not ideal, right? My draw is not ideal because I must have Vx exactly in the horizontal and Vy at that moment exactly in the vertical. As we saw in the projectile motion exercise in the class today, the horizontal velocity projection is always the same, doesn't change. And in this case, is not zero. So the velocity is not vertical either. It has two components. One is the vertical and has a horizontal one. Its vertical velocity component is the same as it was just as it was launched. That's not true. It might be, in fact, is not anywhere. The speed might be the same here, right? At the same level. The speed is the same, but not the velocity. The velocity at this point is downward. The projection of the velocity along the vertical direction is downward, which means negative, right? So right here is positive. Positive. So if you go better like that. So the projection is a positive number, but when it goes down right here, the projection is negative. Its horizontal velocity component is the same as it was just. This is a good one. This is a good one. Its speed's the same. No, it's not. Its speed changes all the time. I'm not gonna do this. You walk 33 meters. I think I did that in class. But one of your classmates and I, in fact, didn't get the solution. So let's try to do again. See if I did something that was not correct, or I did this one. No, I did the other one. Yeah, I did this one. So let's try this one. Orientation. Let me take a different color. Here's the north, south, east, and then west. You walk 53 meters to the north, and then you go 53 meters right here. That's your first vector, first one, 53 meters. And then you turn 60 degrees to your right. So and walk 45 meters. So 60 degrees is pretty much this. To your right, that's what we do. So 60 degrees right here. And then you walk, this is 45 meters. So, and determine the direction of your displacement vector and express your angle, your answers as an angle relative to east. So we have to find an angle relative to east. So you go like this, right? And the answer is we wanna find this angle over here. So we don't know the angle, theta. So what is our run? Let me put the run in a different color. In red, here's the run. And what is the rise? Here's the rise. And our displacement vector in blue is right there, which is given by summing up the green vectors. This one, the first displacement, and the second displacement, okay? So let's find out what is the run and what is the rise. So the run is equal to 45 cosine of 30. So the angle it makes with the horizontal, this angle is 30 degrees. Okay. And the rise is the whole thing over here, right? This rise is 53 plus 45 cosine of 60. So what is the angle? Tangent of this angle is equal to rise over run is equal 45 cosine of 30. Sorry. Is equal rise over run 53 plus 45 cosine of 60 divided by 45 cosine of 30. The components of vectors a and b are given: ax, ay, bx, by. What is the magnitude of the vector difference? So if you want to represent these vectors just for practicing, so ax is 7.6, so it's something that 1, 2, 3, 4, 5, 6, 7. And ay is negative 9.2. 1, 2, 3, 4, 5, 6, 7, and 9.2, right? Here's your vector a. That's your vector a. The vector b is negative bx negative 5.1. 1, 2, 3, 4, 5. This is x, this is y. And the by is negative 6.8. 1, 2, 3, 4, 5, 6.8. So here's the vector b. So we want to find b minus a, right? So geometrically speaking, how do we do b minus a? Well, the minus a vector is this vector over here. This is the minus a vector, okay? So b minus a is the same thing as b plus that vector that I just draw, which means geometrically speaking would be something like this, plus you want to take now negative a and bring it on, and here would be a difference, okay? this vector, this is A, this is negative B, this is A minus B. Okay. Now, how do you find the magnitude? Well, if the projections are given, it's much simpler. So you think about C is B minus A, right? Which means, what is B? B is negative 5.1 in the direction X minus 6.8 in the direction Y. So here's my vector B, minus, what is my vector A? 7.6 in the X direction, minus 9.2 in the Y direction. So C is going to be given by, now you group them in the X component. You group them in the X component, negative 5.1 minus 7.6 in the X direction, plus, and you group them in the Y direction, negative 6.8 minus minus with minus gives you a positive number, 9.2. This is in the Y hat direction. Okay. How do we find the magnitude? So let's keep operating. So negative 5.1 with negative 7.6 is negative 7, 12 in the X direction, plus 9.2 minus 6.8 is 4, 2 in the Y direction. So the magnitude of this vector C, then you apply Pythagoras, the square root of the negative 12.7 square plus 2.4 square. And if the angle were asked, so tangent of the angle between those two would be the rise over run. In other words, 2.4 divided by negative 12.7. Then you would find which angle that represents. So I'm not going to do that one. You can work. If you can do, just let me know. How about this? A vector A has a magnitude of 4 meters and points. Okay, let's get our Cartesian coordinate system. That's the north, that's the south, east, and west. Vector A, magnitude 4, 30 degrees south of east. This is east. South of east, we go 30 degrees. Okay, 30 degrees. And the magnitude of it is 4 meters. So if you measure the length of this vector here, is 4 meters. Okay. And vector B, that's a vector A, in fact, A. Vector B has a magnitude of 2 meters and pointed 30 degrees north of west. So this is west. 30 degrees north is something like this. 30 degrees north of it. In fact, these angles are the same. See that? Congruent. So it's just a line. But this is B. That is B. Oops. Is 2 meters. So A plus B. So if you look at the design here, so A pulled 4 meters to the right, you know, that direction here, right? That direction. And it's like a tug of war. And B is that way. So the resultant of those two, the resultant would be 4 minus 2 meters in that direction, which means 30 degrees, 2 meters, 30 degrees south of east. This should be the good one. All right, back. So we have two forces. This number 38. I'm in a park now, so you might have some noise in the background. But there are two forces. They are acting on an object. And this is an example of problems that might happen in chapter 4, chapter 5. But here it doesn't matter because it has to do with vector addition. And forces are vectors, so when you add them in the way we are learning in chapter 3. So we want to find the magnitude of resultant force. So each of these forces have projections in the x direction and in the y direction. So bring your Cartesian axis, and then you find what are the projection of F1, let's say, in the x direction. So what is the run of this force? Well, the run is 120 cosine of that angle 50 in the x direction. And what is the rise of this force? The rise of the force is positive 120 sine of 50. Sine of 50. This is in the y direction. So, and how about F2? So what is the rise of F2? So F2, considering x direction as positive to the right, F2 projection, the rise is to the left, is negative. Negative 80 cosine of that angle, I barely can read, I think is 72, I think, whatever. In the x direction is negative, indicate to the left, plus the projection of F2, the rise of F2 is positive 80 sine of 72, and in the y direction. So when you add those two components, the resultant of these two forces, or adding them up, you add the coefficients. You add the coefficients minus 80 cosine of 72. This is in the x direction, plus 120 sine of 50 plus 80 sine of 72. Sorry, I'm putting everything together in the y direction. So the magnitude would be the square root of this number square plus, just apply a Pythagoras to it, plus this number square. That's the magnitude. And direction would be tangent is the rise over run. And then you have to see the rise, as you can see over here, is positive. But I don't know about the run. The run, I don't know if it's going to be positive or negative. You have to do an analysis here. So if it's positive, then this vector is above the x-axis. And if this result is negative, it means it's so positive, the resultant will be in that direction. If it's negative, the resultant is going to be in that direction. But based on the size of these vectors, I think it's going to be this way. See a little bit of rotation. A runner runs on a circular path of radius 10 meters. So radius is 10 meters. This is 10, right? 10. what is the magnitude of the displacement of the jogger if he runs halfway around the track? So if he goes and run halfway around the track, so it stops right there, right? So initiated here and finally there. What is the magnitude of the displacement? So this is what it is. The magnitude is twice the radius, 20 meters. What is all the way around the track? So if you go all the way around the track, it goes back to its original point. Displacement is 0. Okay. A girl throws a rock horizontally with a velocity of 10 meters per second from a bridge, and it falls 20 meters. The water below, how far does the rock travel horizontally before striking the water, assuming negligible air resistance? So let's do a little sketch. Throw horizontally. What does it mean? It goes like this. With a velocity of 10 meters per second. From a bridge, it falls 20 meters to the water below. So you have a water right there. And this height is 20 meters. And how far does the rock go? So if you are to describe the path of this rock, something tangent in there, and then it goes, and then splash. Okay, it falls in the water. So you want to find exactly, you want to find this, the horizontal displacement. Okay. And then first, one of the first steps is to identify this situation as a projectile motion situation in which the velocity vector has a run, the initial velocity vector has a run, but doesn't have a rise, which means your v naught x is the same as the initial velocity, 10 meters per second, and your v naught y is none. So you don't have that. It's different from the problem we did in class. The initial vector, velocity vector, had an angle with respect to horizontal, which would imply the existence of a v naught x and a v naught y, right? So you don't have this, right? Because this vector is down. So your v naught x is the 10 meters per second. So, and we want to find x. So in this type of problem, there are two situations. One, the projection in x is such the movement has constant velocity. V is equal v naught x versus time, which means x is equal 10, because it's given, versus time. So if we knew how long it took the project to hit the ground or the water, then the problem would be solved. You would plug your time in seconds over here, and then you have x. But we don't know that. So what do? We go to the other projection, the one in y. The y projection is such, the basic equation describes its motion is final position minus initial position is equal initial velocity in y t minus half 9.8 t squared. So it is said the height of this cliff is, or the height of this bridge is 20 meters. So when the rock hits the water, the y position is 0, and the initial position is 10 meters. So we can take care of the left-hand side of this equation. The initial velocity in y, as we saw here, is 0. And then this is equivalent to 9.8 divided by 2. Negative 9.8 divided by 2 is 4.9 t squared. Right? So the negative cancels with negative. T squared is equal to 10 divided by 4.9, and then we can find t as the square root of 10 divided by 4.9 in seconds. So once we find the time, what do? Plug it in here, and then we can find the horizontal displacement of that rock. I think we did this in class. How about this? I show in the figure the projectile is fired at time t equals 0 from point 0 at the upper edge of a cliff with the initial velocity components given. So v naught x is equal 30 meters per second. So we can even write here our x projection. So all the information in x projection. The projection that has to do with the x direction and y direction. We can also write this given information v naught y is equal 300 meters per second. The projectile rises and then falls into the sea at point P. The time of flight of the projectile, so t, is 75 seconds, no matter if seen from the x or y projection, the time is the same, it doesn't matter. And air resistance is negligible. At this location, gravity is given. What is the horizontal distance d? Well, we know that d is equal v times t, right? So that's it. So then we got it, meters. That's it. So we don't need that information at all. How about this? Projectile is launched with an initial velocity of 80 meters per second. So let's do the sketch. This angle represents 30 degrees. This vector, which is the initial velocity, is 80 meters per second, 30 degrees above horizontal, which means if I bring color into perspective, my v naught x is given right here. V naught x, which is equal to 80 cosine of 30. And here's my v naught y, which is 80 sine of 30. What is the horizontal component of the projectile acceleration? Whew. What is the horizontal component of the projectile acceleration? So the vertical component is, we know, right? That's the vertical component, 9.8 meters per square second. But the horizontal component is none. There is no acceleration in there, right? There's no acceleration in there. It's kind of a tricky one, that one. Oh, that's it. Okay, so let me see the last one here. A hobbyist launches a projectile from ground level on a horizontal plane. It reaches a maximum height. So let's think about it. 72, so maximum height. Maximum height is 72.3 meters. And then it lands x max is 111 meters. So if we were to sketch this situation, so this is the point where the projectile is launched, right? It has an initial velocity. We don't know what it is. It's not given. But we know it goes like this, maximum height, and then falls down. So this is given. This is given. And not only that, this is also given. 1 meters. So how can you make sense of it? What is the angle of launch? So we want to find this angle here, theta. How do we figure that? Well, when we do projectile motion, we know that we break down our problem into major components: x projection and y projection. In x projection, x is equal v naught xt. So x, which is 1, 1, 1, is equal v naught x versus time. So we don't know the time, and we don't know v naught x, so we are pretty much stuck. So how about y? Y minus y naught. So the displacement in the vertical direction. So the displacement is such that you go up and down. So in the y direction is 0, right? Or you could say the final position is 0, the initial position in y is 0. This is equal to v naught yt minus half g t squared. So we can simplify one of the t, and then we can find that time is equal to 2 v naught y divided by 9.8, right? So we can get that. But we haven't used that information of the maximum height yet. So how can we use that information? So we know that when we use Bernoulli equation in the projectile motion, when the displacement is given and information about the velocity is given, we can determine the initial velocity along that direction with motion with acceleration. So if you look at your y direction here, Vy final square, this is Bernoulli equation, is V naught y initial square minus 2 times acceleration times the displacement in y, which is 72.3. Since the final velocity at this point is 0, in free fall the maximum velocity at the highest point is 0, implies this is 0, which means we can find our initial velocity in y. So v naught y is equal the square root of 2 times 9.8 times 72.3. So essentially what I did, I add to both sides of the equation 2 times 9.8 times 72.3, and I took the square root of it, which enabled me to calculate v naught y. Once I calculate this v naught y, I can plug it in here and find t. And once I have t, I can plug it in here and find v naught x. So now look at this. This is my v naught x. This is my v naught y. And this is the angle we want to find. So tangent of that angle, SOHCAHTOA, is v naught y, the rise, over v naught x, and then we could solve. Okay. So this problem has 3 steps solution. projectile motion has always two-step solution. You have to go from X to Y or vice versa. But this problem has another step because the initial velocity is not given, and that complicates a little bit. All right, good luck to you. If you guys, if you don't understand something in there, just let me know. Here's what I recommend. Oh, I should have said that in the beginning. I will go back there. Okay, bye.